Tonight, we're going to confront something that science fiction has been quietly hiding from you for decades. Warp drive. The idea that we could fold space, bend the fabric of reality itself, and cross the void between stars in days instead of millennia. It's the dream that makes every starship feel possible, every alien world feel reachable, every corner of the galaxy feel like it's just a jump away. But here's what's going to shatter everything you thought you understood about interstellar travel. Even if we build it, even if we crack the physics, even if we solve every engineering problem that currently makes warp drive impossible, the distance between stars doesn't care. It has already set traps we haven't talked about. Problems that live deeper than propulsion. By the end of tonight, you're going to understand why warp drive was never the answer we imagined it to be, and why the gap between us and the rest of the galaxy runs deeper than any equation can fix. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The nearest star to our Sun is a small red dwarf called Proxima Centauri. It sits in the constellation Centaurus, visible from the southern hemisphere on a clear night, burning dimly at about 1/800th the luminosity of our Sun. It is our closest neighbor in the entire galaxy. Everything else, every other star, every other system, every other sun in the Milky Way is farther. The distance to Proxima Centauri is 4.24 light-years. That number doesn't feel threatening at first. 4.24. It sounds manageable. It sounds like something you could cross. But a light-year is the distance light travels in one full year, moving at 186,000 miles per second. In 1 second, light could circle the entire Earth more than 7 times. In 8 minutes, it crosses from the Sun to our planet. In 1 year of continuous travel, it covers about 5.9 trillion miles. 4 light-years is approximately 25 trillion miles of empty space. Voyager 1 has been flying since September 19th, 1977. It is the most distant human-made object in existence. It crossed into true interstellar space in 2012, passing the heliopause, the boundary where the Sun's particle wind gives way to the interstellar medium. After 35 years of continuous travel, Voyager 1 is moving at roughly 38,000 miles per hour. That's fast by every human standard. More than 20 times the speed of a rifle bullet. Fast enough to circle Earth in under 40 minutes. At that speed, heading toward Proxima Centauri, the crossing would take approximately 70,000 years. 70,000 years at the fastest speed we have ever achieved. And Proxima Centauri is the closest one. Now, the obvious response to this problem is that we need better engines. We need propulsion that makes chemical rockets look like a match next to a nuclear reactor. That's true. Physicists and engineers have spent decades working on exactly this. Nuclear pulse propulsion, fusion drives, antimatter engines, light sails accelerated by massive ground-based lasers. All of these could, in principle, get a spacecraft to a meaningful fraction of the speed of light. 10%, maybe 20%. At 10% of light speed, the crossing to Proxima Centauri takes 42 years. At 20%, about 21. At 50%, which is probably beyond anything we could build for centuries, about 8.5 years. These are real numbers. They represent the kind of progress that changes the character of the problem. 70,000 years becomes 40. That's a transformation, not an improvement. But these numbers also reveal the wall that exists on the other side of faster propulsion. Getting to 10% of light speed requires enormous energy. Every additional fraction of velocity costs exponentially more. Albert Einstein's theory of special relativity, published in 1905, showed that, as an object approaches the speed of light, its effective mass increases. At 99% of light speed, the apparent mass of a spacecraft has grown by a factor of 7 compared to what it was at rest. At 99.9% of light speed, by a factor of 22. To actually reach light speed would require infinite energy. The universe doesn't have infinite energy to give you. So, conventional propulsion, no matter how advanced, runs into this wall. You can get close. But close costs more than almost anything civilization could produce. And this is exactly where warp drive enters the conversation. Not as fantasy, as a genuine response to a real mathematical problem, as a way to ask a different question entirely. In 1994, a physicist named Miguel Alcubierre was working at the University of Wales and asked a question nobody had formally put to Einstein's equations before. Einstein's relativity forbids objects from moving through space faster than light. But what if space-time itself moved? What if, instead of pushing the ship through the universe, you arranged for the universe to carry the ship? He worked through the mathematics. The equations permitted it. Alcubierre published the result in Classical and Quantum Gravity in 1994 in a paper called The Warp Drive: Hyper-Fast Travel Within General Relativity. The concept was a bubble of flat space-time surrounding the ship. Ahead of the bubble, space compressed toward the destination. Behind it, space expanded away from the origin. The ship sits still inside, feeling no acceleration, no g-forces, no time dilation. The bubble moves through space-time. The ship rides it. And because space-time itself is doing the moving, not an object traveling through space-time, the light speed limit doesn't apply in the same way. The bubble could, in principle, move faster than light. Much faster. Star Trek made this look like a button press. What Alcubierre showed is that the underlying idea isn't fiction. It's mathematics. And mathematics has to be consistent with everything else that's true. The physics community found no error in the equations. But the requirements were severe. To generate that geometry, you'd need matter with negative energy density, energy below zero. Exotic matter, something never observed in any laboratory anywhere on Earth. The energy requirement was also staggering. Initial estimates put it at roughly the mass energy equivalent of Jupiter, converted entirely into exotic negative energy, just to sustain a bubble barely large enough for a spacecraft. The mass of an entire planet, for one small room of flat space-time. This is where the science fiction version of the story usually stops. What it misses is what happened in the decades after. In 1999, a physicist named Harold van den Broek proposed making the bubble's outer surface microscopic while keeping the interior spacious. General relativity permits this. The geometry inside a warp bubble doesn't have to match the geometry outside. That single change brought the exotic matter requirement down from the mass of Jupiter to roughly the mass of a small bacterium. Still exotic matter. But the direction of travel was now clear. The energy budget wasn't a fixed physical minimum. It was a consequence of the geometry Alcubierre happened to choose. Change the geometry, and the number changes with it. In 2011, Harold White at NASA's Eagle Works lab changed it further. A toroidal shell instead of a thin sphere, with an oscillating intensity rather than a fixed one. His calculations reduced the requirement to hundreds of kilograms on paper. His experimental program to detect spacetime curvature effects produced inconclusive results and eventually lost momentum. But the theoretical trajectory was unmistakable. From the mass of Jupiter to a bacterium to hundreds of kilograms. Still impossible to build, but no longer cosmically absurd. Engineering absurd is a different thing. In 2021, Alexei Bobrik and Gianni Martir published a framework that reorganized the entire field. They showed that every warp drive ever proposed fits into the same three-region structure: outer flat spacetime, inner flat spacetime, where the crew lives, and a transition shell doing all the work in between. By mapping the full design space, they found large territories no previous paper had explored. One of the most important was subluminal warp bubbles, bubbles that move slower than light. Most of the field had spent 30 years chasing superluminal designs because faster than light was the whole point. Bobrik and Martir pointed out that subluminal bubbles might satisfy energy conditions that exotic matter violates, potentially requiring no negative energy at all. And they'd still be transformative. A subluminal warp bubble at 90% of light speed would cross the solar system in hours and reach Proxima Centauri in about 5 years, with no forces transmitted to the crew whatsoever. They also prove something fundamental about the mechanics. A warp bubble still needs conventional propulsion to accelerate up to speed. It changes what the propulsion is pushing the shell, not the crew, but the energy has to come from somewhere. Warp drive isn't a free energy machine. It's a specific space-time geometry that, once in motion, carries everything inside it. Then, in April 2024, the applied physics team published something that moved the entire conversation forward. A paper in Classical and Quantum Gravity titled Constant Velocity Physical Warp Drive Solution. The authors presented a warp drive design that satisfies every classical energy condition: the weak energy condition, the null energy condition, the dominant energy condition, the strong energy condition. No exotic matter anywhere in the structure. No negative energy. Ordinary baryonic matter, the stuff that makes up stars and planets, and you arranged in specific configurations. The mathematics was valid. The physics community acknowledged the result. But the paper carried a caveat that most headlines missed. This design is explicitly subluminal. It does not break the speed of light. It does not get you to Proxima Centauri in days. What it does is prove that warp spacetimes don't inherently require exotic matter, at least below the speed of light. That is a genuine and meaningful result. But it also reveals something important about where the warp drive story actually stands. And it sets up every problem we haven't yet talked about. Here is the first one. Even a working subluminal warp bubble, perfected, engineered, operating exactly as the equations describe, doesn't eliminate the interstellar crossing. It just makes the crossing faster. The 4.24 light-years between us and Proxima Centauri remain 4.24 light-years. The ship still has to traverse every inch of them. Every cubic meter of interstellar space. Every magnetic field. Every stray particle launched from some distant stellar event. Warp drive, in every realistic formulation we have, doesn't fold space so that two distant points become adjacent. That's a wormhole. entirely different physics. Entirely different, and arguably much harder problems. Warp drive moves a bubble through space at high speed. The space has to be crossed, and the interstellar medium, as empty as it sounds, is not nothing. Between the stars, there is gas, mostly hydrogen, mostly ionized in some regions, neutral in others. There are magnetic fields threading through it, produced by the collective motion of charged particles over vast timescales. There are cosmic rays, high-energy particles, accelerated by supernovae, pulsar winds, and black hole jets streaming through the interstellar medium in all directions continuously. On average, the interstellar medium contains about 1 atom per cubic centimeter. That sounds trivially sparse. The air you're breathing right now contains roughly 25 quintillion molecules per cubic centimeter. The interstellar medium contains 1 atom, but cross 25 trillion miles of it, and the numbers accumulate. At any meaningful fraction of light speed, the leading edge of the warp bubble encounters this material. The bubble's geometry interacts with the surrounding medium. At high speeds, this interaction produces electromagnetic effects. The details of exactly how a warp bubble's leading edge interacts with interstellar gas and dust depend on the specific design of the bubble, its shape, its speed, the structure of its transition shell. These interactions are an active area of research. They're not fully worked out, but the medium is there. It doesn't vanish because you designed a better engine. It has to be accounted for in any realistic mission profile. The second problem is navigation. Stars are not sitting still, and neither is the Sun. Proxima Centauri is moving through the galaxy at roughly 1.4 miles per second relative to our Sun. It's also gravitationally bound to the Alpha Centauri system. 2 Sun-like stars designated Alpha Centauri A and Alpha Centauri B orbiting each other, with Proxima orbiting that pair at a vast distance. When you aim a spacecraft at Proxima Centauri, you're not aiming at where it currently appears in the sky. You're aiming at where it will be when you arrive. For a 42-year crossing at 10% of light speed, predicting the star's position requires modeling its trajectory decades into the future. Gravitational perturbations from surrounding stars introduce uncertainty. The local interstellar medium creates slight effects on the ship's trajectory over time. Course corrections require propellant. And every kilogram of propellant for mid-course corrections is a kilogram that had to be accelerated from rest at launch. The rocket equation doesn't care how clever your engine is. More mass you need at your destination means more mass you need at departure, which means more fuel to accelerate the fuel, which means more structure to hold the fuel, which means more fuel to accelerate the structure. The scaling is exponential. Warp drive changes the nature of this problem. If a warp bubble can adjust its path with geometric changes rather than propellant expenditure, navigation becomes more manageable. But the fundamental challenge of hitting a moving target at the end of a years-long crossing remains. Physics doesn't issue exceptions for clever engineering. The third problem is specific to faster-than-light warp bubbles, and it's severe enough that many physicists consider it a fatal flaw for the superluminal design. When a warp bubble moves faster than light, it creates a causal horizon at its leading edge. A causal horizon is a boundary in spacetime across which information cannot propagate in a given direction. You know the most familiar version of this. A black hole's event horizon. At a black hole, spacetime is falling inward faster than light can propagate outward. Anything crossing that boundary cannot escape, not because some enormous force is holding it, but because every possible future path through the geometry points inward. There is no direction to move that leads back out. A superluminal warp bubble generates an analogous structure at its front wall. The leading edge of the bubble is moving forward faster than light. Any signal sent from inside the ship toward the front of the bubble, any information, any course correction, any command cannot catch the leading edge. The edge is receding faster than the signal can travel. This creates a control problem that is not an engineering inconvenience. It is a structural feature of superluminal geometry. You cannot steer from the inside. You cannot adjust the bubble's path once it has exceeded light speed. You cannot turn it off from within. Whatever trajectory the bubble is on when it goes superluminal, it stays on. There is no mechanism available to the crew to change it. Mission planners sometimes refer to this as the horizon problem. Not a navigational difficulty you work around with better instruments. An inherent property of the geometry itself. A superluminal warp bubble, once launched, operates autonomously in a way its occupants cannot override. There is a related consequence. Particles from the interstellar medium accumulate at the leading edge of a superluminal bubble. They cannot escape forward, the bubble is outrunning them, and they pile up against the front of the transition shell. This buildup grows throughout the crossing. When the bubble finally decelerates back to subluminal speed at its destination, those accumulated particles are released. All at once, in the forward direction. As a focused burst of high-energy radiation, aimed directly at whatever the bubble just arrived near. This was formalized in 2009 by Stefano Finazzi, Stefano Liberati, and Carlos Barcelo. They showed that a spacecraft decelerating from superluminal warp speed would release an intense pulse of high-energy radiation at the moment of slowdown. Depending on the design and the crossing distance, the burst could be energetic enough to be dangerous to anything in the path ahead, including the destination. You arrive, and you irradiate it. You cannot warn anything or anyone ahead that you're coming, because your signal cannot outrun the bubble. You cannot send a warning that you're slowing down, because the leading horizon traps every signal you produce. This isn't a theoretical concern that better shielding on the destination end would fix. It's a consequence of the geometry of superluminal travel. It's baked into the structure of the spacetime metric. There is a clear way around the horizon problem. Stay subluminal. A warp bubble moving slower than light does not generate a causal horizon at its leading edge. The interior of the bubble remains causally connected to the front wall. You can steer. You can adjust the trajectory. You can slow down without releasing a focused radiation pulse. This is one of the primary practical advantages of the subluminal class of warp drives that Bobrick, Martier, Fuchs, and the applied physics team have developed. No horizon problem. No particle accumulation at the leading edge. Fully controllable. But subluminal also means no faster-than-light travel, which means every subluminal warp drive, no matter how close to light speed it operates, is still crossing real interstellar distance at sublight speeds. Still taking years to reach the nearest star. Still taking decades to reach anything farther. The galaxy has about 100 billion stars. The Milky Way is roughly 100,000 light-years in diameter. A subluminal warp bubble at 99% of light speed would take roughly 100,000 years to cross from one end of the galaxy to the other. From the crew's perspective, due to time dilation, it would feel shorter. But Earth would have aged 100,000 years regardless. The galaxy isn't smaller because you're moving faster. It remains exactly as large as it always was. Time dilation itself deserves a careful look, because this is where the interstellar distance problem becomes strange in a different way. Einstein's special relativity contains a prediction that has been confirmed in every experiment designed to test it, from particle accelerators to atomic clocks on GPS satellites to observations of cosmic ray muons produced in Earth's upper atmosphere. Time passes more slowly for objects moving at high speed relative to a stationary observer. This isn't a perception. It isn't an artifact of measuring instruments. It is a fundamental feature of how time works in the universe. At everyday speeds, the effect is immeasurably small. At 10% of light speed, it's measurable but modest. At 90% of light speed, the difference becomes profound. A spacecraft traveling at 90% of light speed for 4.24 light-years, as measured by observers on Earth, would cover that distance in about 4.7 Earth-years. But inside the ship, less time would pass. The crew would experience roughly 2 years of subjective time. The faster you go, the more pronounced the effect becomes. At 99% of light speed, an astronaut could cross the 4.24 light-years in about 7 months of ship time, while 4.4 years pass on Earth. At 99.9% of light speed, ship time compresses further. This sounds like a solution, and in a specific sense, it is. The crew can traverse enormous distances within a single human lifetime. A traveler at extremely high speed, not warp drive, just very fast conventional relativistic flight, could theoretically cross hundreds of light-years within their own lifespan. But here's the trap. Earth doesn't share the ship's time dilation. Every year of ship time at high speed corresponds to many more years on Earth. Go fast enough, far enough, and you return to a planet that has aged centuries. Everyone you knew is gone. The civilization that sent you has changed in ways you couldn't predict. Your place in the culture you left is defined by your absence rather than your presence. Warp drive, in the Alcubierre formulation, was specifically designed to avoid this problem. Inside the bubble, local spacetime is flat. The crew experiences normal time. And because the bubble's motion is spacetime itself moving, rather than the ship moving through spacetime, time dilation doesn't accumulate the same way. You arrive at your destination with something close to the same amount of time having passed as elapsed back on Earth. This is a genuine advantage of the warp drive concept over conventional relativistic travel. But it only fully applies if you exceed light speed. A subluminal warp bubble, moving at 90% of light speed, still accumulates time dilation less than a conventional spacecraft at the same speed, because of how the bubble geometry affects local measurements. But some dilation still occurs. The details are design-dependent. The point is that even with warp drive, the time problem doesn't simply vanish. You still have to choose which version of it you're willing to accept. Faster means more Earth time passes. Staying connected to Earth, time means slower. The distance is the constraint. Every proposed solution trades one version of the problem for another. The energy question sits beneath all of this, and it doesn't get discussed honestly enough. Not the conceptual energy required by warp drive, the actual power output needed to generate, sustain, and control a warp bubble during an interstellar transit. Even the most optimized subluminal warp design requires continuous energy input to maintain the bubble geometry against the tendency of spacetime to relax back toward flatness. You're not coasting through space. You're holding a specific spacetime configuration in place against the universe's preference for simpler geometry. for the entire crossing. Years. The specific numbers depend on the design, and the Fuchs 2024 paper reduced some requirements significantly compared to earlier work. But even conservative estimates for near-light-speed subluminal warp bubbles place the sustained power requirement in ranges that dwarf anything our civilization currently produces. Current global electricity generation across all of humanity is roughly 30 terawatts. Some warp drive designs require sustained power comparable to significant fractions of that figure, focused precisely, maintained without interruption for the entire mission duration. The most optimized designs currently described in peer-reviewed literature assume energy sources that don't exist yet. Controlled fusion. Potentially antimatter. Power systems that are speculative, even by the standards of advanced technology planning. Building a warp drive isn't purely a physics problem anymore, at least not for the subluminal case. The physics has been established in broad outline. What remains are engineering problems, and an energy problem, and a materials problem. The shell that creates and maintains the warp geometry must withstand stress regimes far beyond anything we can currently produce or even specify precisely. Materials that can maintain precise geometric configurations under extreme thermal and gravitational loads for years at a time, with no opportunity for maintenance. Nothing like that currently exists. Nothing in our materials science pipeline is clearly heading toward it. The timeline that physicists who work seriously in this field discuss honestly, without exaggeration or inflated optimism, is not decades. It's centuries, probably several of them. Here's where the conversation usually ends, and where it actually has to continue. Because, assume we solve all of it. Assume we crack the energy problem, build the materials, demonstrate the warp effect in a laboratory, scale it up, iron out the engineering, and eventually launch a working subluminal warp bubble toward Proxima Centauri. What does the crossing actually look like? The bubble accelerates away from the solar system. It clears the heliopause in minutes, rather than the 35 years it took Voyager 1. It enters the true interstellar medium, the thin gas and magnetic fields between stars. The bubble's geometry interacts with this medium in ways that depend on its specific design. The leading-edge physics has to be worked out for each geometry. Electromagnetic interactions from ionized interstellar gas affect the bubble structure. These are engineering problems with engineering solutions. But each one adds complexity, power draw, and failure modes to the already demanding challenge of the vehicle itself. Deceleration at the destination has to be controlled precisely. The spacetime geometry that was compressed ahead of the bubble and expanded behind it has to transition back to flat. That transition has to happen gradually enough that the crew inside isn't affected by sudden geometric discontinuities. It has to happen in the right location, aimed at where the star system actually is when the bubble arrives, not where it appeared to be when the mission launched years earlier. None of this is physics, impossible, but none of it is solved. All of it has to be solved simultaneously before a single warp ship goes anywhere. Now let's be specific about a number that doesn't appear often enough in these discussions. The nearest star is 4.24 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years away. Tau Ceti, one of the nearest sun-like stars with confirmed planets, is about 11.9 light-years. Epsilon Eridani, another nearby star of considerable interest for its planetary system, is 10.5 light-years. These are the closest stars, our immediate neighbors. They all require years of travel, even at light speed. Most of the galaxy's genuinely interesting systems are much farther. TRAPPIST-1, the star with 7 Earth-sized planets, including several positioned in the habitable zone where liquid water could exist on the surface, is about 40 light-years away. 40 light-years is the closest genuinely exciting target for life searches. A subluminal warp bubble at 99% of light speed takes about 40 Earth years to reach it. From the crew's perspective, somewhat less. But the ship still has to be there for those 40 years. The crew still ages. The mission still has to be sustained for that duration. And TRAPPIST-1 is the optimistic, nearby case. Kepler 452, one of the more publicized Earth-like planet candidates, is roughly 1,400 light-years from Earth. At 99% of light speed, that's approximately 1,400 Earth years. There is no version of subluminal warp drive that makes Kepler 452 accessible on a human timescale. For a superluminal design, if the physics ever allows it and the horizon problems are solved, the crossing time shortens dramatically. Weeks instead of years, potentially. Days instead of decades. That would be transformative. But the superluminal design is the one that currently requires exotic matter we can't produce, horizon physics we can't resolve, and radiation effects we can't neutralize. The subluminal design is the one that might actually be buildable. And the subluminal design still has TRAPPIST-1 at 40 years. There's a concept in physics called the Fermi paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory and asked a question that has never been satisfactorily answered. If the galaxy is old enough that technologically advanced civilizations could have arisen billions of years ago, and if interstellar travel is possible, even at modest fractions of light speed, where is everyone? The Milky Way is roughly 13 billion years old. Stars capable of supporting complex chemistry on orbiting planets have existed for billions of years. Even at 1% of light speed, a civilization that began expanding 500 million years ago could have established a presence in every corner of the galaxy by now. The galaxy should be saturated with evidence, signals, mega-engineering projects visible across light years, modified stars, Dyson spheres. At minimum, a strong radio signature from civilizations spread across thousands of star systems. We see none of it. The silence is complete. One of the more sobering possible answers is that the distance between stars is itself a filter. That interstellar travel isn't just hard for us. It may be hard for everyone. The same physics applies everywhere in this galaxy. The same light speed limit, the same rocket equation, the same energy requirements. Any civilization on any planet orbiting any star faces identical fundamental constraints. The distance between stars is not a human problem. It is a universal condition, a property of the universe that applies equally to every intelligence that has ever or will ever develop anywhere. And if the barriers are high enough, then civilizations develop and end in isolation. They listen, they transmit, they reach toward the stars, and they never cross. This doesn't mean warp drive is impossible. Alcubierre's mathematics is real. The Fuchs 2024 result is published and valid and standing. The subluminal path exists in the equations. Research continues, year by year, refining the designs and reducing the theoretical requirements. But the Fermi paradox suggests that if anyone had cracked the distance problem across the billions of years this galaxy has been here, we'd know. The sky would look different. It doesn't. Here's the uncomfortable version of that thought. If warp drive is real mathematics, if the physics genuinely permits it, why hasn't it shown up as evidence of other civilizations? Maybe the energy barriers are insurmountable, even for advanced civilizations. Maybe additional physics we haven't discovered imposes constraints the current equations don't capture. Maybe the civilization that finally builds a warp ship doesn't go where we'd expect. Maybe the light from their departure won't reach us for millions of years. All of these are consistent with what we observe. But so is the simplest explanation: that the distance between stars defeats every civilization eventually, that it's not a problem waiting for the right solution. It's the boundary condition of the universe we live in, a property of the cosmos that doesn't negotiate with the intelligence that developed within it. Here's something that gets lost in all the physics. Even if the superluminal warp drive problems were somehow solved, exotic matter produced, horizon physics resolved, radiation burst, neutralize the distance between stars, still sets the terms of every crossing. You're still going somewhere specific, still departing from a real location, still arriving at a real star with a real planetary system and real conditions, still spending real time in transit, even if that time is weeks rather than years. The universe hasn't been compressed. The stars haven't moved closer. The distance hasn't changed. Warp drive speeds up the crossing. It does not eliminate it. And for the distances that actually matter, the distances to the stars, where life might exist, where habitable planets orbit, where civilizations might have developed, those distances are tens, hundreds, or thousands of light years. Even at 10 times the speed of light, crossing to a system 100 light years away takes 10 years. Even at 100 times the speed of light, crossing to a system 1,000 light years away takes 10 years. The galaxy is big enough that speed alone never fully closes the gap. There will always be distances that defeat any finite crossing speed. And the galaxy contains 100 billion of them. Now think about what warp drive actually does well, even in its current theoretical form. A subluminal warp bubble transforms travel within the solar system. Right now, a mission to Mars takes 6 to 9 months, depending on orbital geometry. A mission to Jupiter's moons takes years. The outer planets require decades with conventional propulsion. A warp bubble would cross the entire solar system in hours. It could reach Mars in minutes. Every corner of our solar system, every moon, every asteroid, every Kuiper Belt object becomes accessible on mission timescales that make crude exploration genuinely practical. The solar system contains enormous complexity we've barely touched. Jupiter's moon Europa, with its subsurface ocean, might harbor microbial life. Saturn's moon Enceladus erupts water vapor from a warm interior ocean. Titan has lakes of liquid methane, a thick atmosphere, and organic chemistry unlike anything else in the solar system. Io is the most volcanically active body in the solar neighborhood. All of these worlds are scientifically extraordinary. All of them are currently reachable only with missions that take years and cost billions and involve robotic probes rather than human researchers. A working subluminal warp drive changes this entirely. You could send researchers to Europa and bring them home within months. You could maintain a rotating scientific presence on multiple moons simultaneously. You could respond to discoveries in real time rather than operating on the 5 to 15-year timescale of conventional deep space missions. This would be an enormous achievement for science. It would make us a true solar system civilization in a way we currently are not. The warp drive's failure to solve the interstellar problem doesn't diminish what it does for the solar system problem. But The interstellar problem is what everyone is really asking about. And on that front, the honest accounting is more difficult. There's a specific physics problem that warp drive introduces even when it works correctly. Consider what happens inside a warp bubble as it crosses interstellar space. The interior of the bubble is flat spacetime, normal physics. The crew lives there, eats there, sleeps there. From their perspective, they're in a room that behaves normally. But the exterior is undergoing dramatic geometric changes. Space is being compressed ahead and expanded behind. The transition shell is maintaining a structured curvature that would, if you were standing in it rather than inside it, feel extraordinarily strange. Now consider communicating with Earth during the crossing. Radio signals are electromagnetic radiation. They travel at the speed of light. A subliminal bubble is moving slower than light, so radio signals from Earth can catch the bubble. You can communicate with a delay that grows as the bubble moves farther away. At 2 light-years into a 4 light-year crossing, signals take 2 years to arrive. The communication delay is the crossing time divided by 2, not instantaneous, not even close. If something goes wrong on the ship, you can't call for help and expect a response in any useful time frame. You're isolated, not by choice, by physics. Earth can send a message, and the crew receives it years later. The crew can send a distress signal, and Earth receives it years later. By the time Earth knows something is wrong, the situation is long past the point where Earth could do anything about it. This is the same isolation that plagued the proposed generation ships of conventional interstellar mission designs. Warp drive reduces the crossing time dramatically. It doesn't change the fundamental physics of signal propagation. Radio waves travel at light speed. Crossing times of years produce communication delays of years. The isolation is built into the distance. The human factor in all of this is easy to underestimate. People are good at abstract distances. We can hear 4.24 light-years and nod as if we've processed it. We haven't. No one has. The number is too large for the biological machinery we use to comprehend space. We evolved to navigate a savanna, to estimate distances across valleys and between trees, to judge the speed of an animal at a few hundred feet. Our intuitions about scale were calibrated for a world roughly the size of a continent. We can think our way beyond those intuitions. We can do the mathematics. We can build the instruments and run the missions and measure the universe to extraordinary precision. But we can't feel it. And the human cost of crossing interstellar space isn't just physical. It isn't just radiation exposure and muscle atrophy and bone density loss, though those are real and serious. It's the sustained psychological weight of isolation in a small space, separated from everyone and everything familiar, for years or decades, with no certainty that the mission will succeed and no ability to return quickly if something goes wrong. Space stations have taught us something about this. The International Space Station has hosted human beings continuously since November of the year 2000. Astronauts spend months at a time aboard it. They develop mental health challenges. They report strong emotions about isolation and confinement. They count the days until return. And the International Space Station is in low Earth orbit, about 250 miles up. Radio contact with the ground is essentially instantaneous. Re-entry takes hours. An emergency can be responded to within days. An interstellar warp crossing is nothing like this. The crew cannot return quickly. The crew cannot contact home and expect a response. The crew is in a small set of interconnected rooms with the same people, the same routines, and the same walls for years. Warp drive shortens the crossing. It doesn't fix what the crossing does to people. The materials and engineering challenges deserve a moment of honest description. What does it actually take to build a warp shell? The shell has to maintain a precise geometric configuration, a specific distribution of mass and energy that produces the desired spacetime curvature for the entire crossing. It has to resist the interstellar medium pressing against its leading edge. It has to handle temperature differentials between the side facing the direction of travel and the side facing the void behind. It has to remain structurally intact under the gravitational stresses produced by its own geometry. It has to do all of this with no possibility of major repair or replacement for the duration of the mission. Materials science on Earth produces extraordinary things. Carbon fiber composites, titanium alloys, advanced ceramics, graphene. Materials with strength-to-weight ratios that would have seemed impossible to engineers a century ago. None of them are sufficient for what a warp shell requires. The stress regimes involved are qualitatively different from anything we've encountered in conventional engineering. We don't have laboratory tests that simulate what a warp shell would experience in operation. We don't have design specifications because we don't have enough understanding of the shell's behavior at operating conditions to write them. We don't know what failure modes look like because we've never built anything approaching a warp shell. This isn't an argument that it can't be done. It's an honest description of where we are. The gap between what we know and what we'd need to know is vast. Not the kind of gap that closes in a decade of focused research. The kind that requires fundamental advances in multiple fields simultaneously, over timescales that dwarf any individual research program. There's another aspect of the interstellar distance problem that warp drive doesn't touch. What happens after you arrive? Suppose the bubble decelerates successfully. The crew finds themselves in the Proxima Centauri system. They have Proxima itself, a red dwarf star with a fraction of the sun's luminosity burning at the center. Proxima b, a rocky planet in the habitable zone, orbiting about 4.5 million miles from the star. Not Earth-like in experience, because the star it orbits flares violently and frequently. Red dwarfs are magnetically active. They produce stellar flares, rapid increases in brightness, and UV and X-ray output far more intense and frequent than our Sun. Proxima Centauri is a particularly active example. Any surface on Proxima b is subjected to regular bursts of high-energy radiation that would sterilize an unprotected environment. Whether Proxima b has any protection, a magnetic field strong enough to deflect the worst flares, an atmosphere dense enough to absorb them, is unknown. We don't know if the planet has liquid water. We don't know if it has the chemistry necessary for life. We don't know its surface conditions. Beyond the rough parameters astronomers have been able to infer from light years away, arriving there doesn't mean arriving at a hospitable destination. It means arriving at a destination we're almost entirely ignorant about, in a system with conditions significantly different from our own. The crew would find something. Whether that something is scientifically valuable, potentially habitable, or something in between depends on physics we can't measure from here. Warp drive gets you there. It doesn't guarantee what's there is worth the crossing. This is true of every interstellar target. The planets of TRAPPIST-1, exciting as they are, might have lost their atmospheres to the active red dwarf they orbit. The planets of Tau Ceti might be barren rocks. The planets of Epsilon Eridani might be bombarded by debris from the dense asteroid belt astronomers have detected there. We're navigating toward the unknown. Warp drive doesn't change that. Here is a dimension of the problem that's rarely discussed in the context of interstellar travel. The galaxy is rotating. The Milky Way is a spiral galaxy, with a central bar of stars, spiral arms extending outward, and a disk roughly 100,000 light-years in diameter. The entire structure is rotating around the galactic center. The Sun orbits the galactic center at about 480,000 miles per hour, taking roughly 225 million years per orbit. In the time our solar system has existed, it has made approximately 20 trips around the galaxy. Stars in different parts of the disk orbit at different rates. Stars near us share similar orbital paths, which is why the nearby stellar neighborhood is relatively stable. Proxima Centauri isn't going to drift dramatically away from us in the next few million years. But the galaxy's rotation means that as you move toward the galactic center or out toward the rim, the velocity structure changes. A warp bubble crossing toward the galactic center would be traversing regions where the background velocity field is different from our local neighborhood. Navigation has to account for this. The target destination has to be modeled not just as a static point in space, but as an object moving through the galaxy's rotating structure. For nearby stars, this is manageable. For stars deep in the galactic bulge or far out on the rim, the motion becomes significant over crossing timescales. This isn't an insurmountable problem. But it's another layer of complexity that the simple version of warp drive, point at a star and engage, doesn't capture. The galaxy is not a static backdrop. It's an active, rotating structure, and any ship crossing it has to navigate that structure dynamically. Here is what the physics community honestly believes right now. Not the popular science version. Not the version that ends with, "But warp drive is possible, so anything could happen." The actual professional assessment. Subluminal warp drive. Moving a space-time bubble at speeds below the speed of light is very probably not forbidden by fundamental physics. The 2024 Fuchs paper demonstrates a valid design using only ordinary matter. It violates no known physical law. It is extraordinarily difficult engineering, requiring sustained power outputs and materials that don't exist yet. But it is not impossible. The physics door is open. The engineering door is closed, for now. Superluminal warp drive, exceeding the speed of light, remains unresolved, and the professional assessment is cautiously pessimistic. No one has published a design that satisfies all energy conditions and moves faster than light simultaneously. Every faster-than-light metric identified so far requires negative energy somewhere. Mathematical theorems, not absolute proofs, but strong constraints push in the direction of impossibility for superluminal designs. Most physicists who work in this area believe superluminal warp drive might be fundamentally forbidden, not by an arbitrary rule, but by the same deep structure of spacetime that produces time dilation and the mass-energy equivalence. The structure woven into reality from its first moments. That might change. New physics is discovered. Frameworks are revised. History has surprised physicists before. But the honest current assessment is that superluminal warp drive faces barriers that look more like fundamental constraints than engineering challenges. The distinction matters. Engineering challenges yield to cleverness and time and resources. Fundamental constraints don't. Papers appear regularly in Classical and Quantum Gravity and Physical Review D on warp drive topics. Conferences on advanced propulsion draw serious researchers. Numerical tools for evaluating warp metrics have been developed by the Applied Physics Group. Graduate students can cite warp drive papers without professional stigma in a way that wasn't true 20 years ago. The field has moved from mathematical curiosity to recognized research program. This is real. The progress is genuine. The trajectory of reduction in exotic matter requirements, from Jupiter mass to bacterium mass to zero for subluminal, is a real intellectual achievement. But the timeline that honest researchers discuss is centuries, not decades. The gap between the best current theoretical result and a working vehicle is as large as the gap between Newton's equations of motion and the first spacecraft. Larger, possibly. Newton's mechanics could be implemented with materials and energy sources that existed in his era. Warp drive cannot be implemented with anything that currently exists. The materials, the power sources, the control systems, none of them are on the shelf. None of them are clearly approaching the shelf. The research is real and valuable. The result is not close. Here is what warp drive doesn't fix, even if it works perfectly. It doesn't fix the communication delay. It doesn't fix the isolation. It doesn't fix the human cost of years in a small space. It doesn't fix the uncertainty about what you'll find when you arrive. It doesn't fix the fact that most of the galaxy's stars are farther away than any crossing time we'd consider reasonable. It doesn't fix the fundamental physics that makes superluminal travel still unresolved. And it doesn't fix the distance. The distance between stars remains what it is, a property of the universe, not a number that yields to clever engineering, not a gap that closes because humanity decides it wants to cross it. 25 trillion miles to Proxima Centauri. Every other star is farther. The distance is the thing that all of this is a response to. And all of the responses, nuclear pulse drives, fusion engines, antimatter, laser sails, Alcubierre metrics, Van den Broek geometries, Fuchs solutions are attempts to make that distance less brutal. Not to make it smaller. It isn't smaller. It's exactly as large as it's always been. You might ask, what happens when we eventually do cross to the nearest stars? Not as a science fiction premise. As a practical question about what interstellar civilization actually looks like. A crossing to Proxima Centauri takes years, even with the best warp drive we can imagine building. The crew arrives. They explore. They find Proxima b. They assess it. They transmit their findings. Those findings take 4 years to reach Earth. Earth sends a response. That response takes 4 years to arrive at Proxima. The round-trip communication delay is 8 years. From the moment you ask a question to the moment you get an answer from Earth, 8 years have passed. Any decision that requires consultation with Earth has an 8-year cycle time. Any emergency that requires external expertise has an 8-year response window. This enforces a radical autonomy on interstellar missions that no amount of better engineering can eliminate. The people at Proxima Centauri are on their own, not because we haven't built a fast enough communication system, because light only moves at one speed, and nothing known to physics moves faster. The crew at Proxima operates with the information they brought, updated by whatever they discover locally, with occasional long-delayed messages from a home civilization that is perpetually 8 years behind on events. This is not like being far from home in any sense we currently understand. It is a fundamentally different relationship to civilization. A relationship defined by distance in a way that distance on Earth never produces. There's a question that persists underneath all the physics. Why does the distance between stars have to be this large? Is it just chance that Proxima Centauri is 4 light-years away rather than 4 light-months? The answer involves how stars form. Stars are born from collapsing clouds of gas and dust, and the physics of that collapse produces stars with minimum separations set by the typical masses and densities of interstellar gas clouds. A cloud massive enough to form one star is also massive enough to form several, and the gravitational dynamics of multiple protostars forming in the same cloud naturally establish separations on the scale of light-years. This isn't fine-tuned. It's a consequence of the basic physics of gas dynamics, gravity, and the temperature of the interstellar medium. The interstellar medium is cold about 10 to 30 Kelvin in molecular clouds, the regions where stars form because it radiates heat away efficiently. The balance between thermal pressure, gravity, and the energy available from molecular hydrogen produces characteristic mass scales and separation distances. If the universe had slightly different fundamental constants, stars might be closer together or farther apart. But in the universe we live in, with the constants that govern it, the distances between stars are what they are. 4 light-years to the nearest neighbor. Not a gap placed there by design or indifference. A consequence of how physics works at scales far above the human. The distance between stars is not a cosmic obstacle course. It's a natural byproduct of the same physics that makes stars exist at all. Perhaps the most important shift that comes from understanding all of this isn't about warp drive. It's about the solar system. The distance between stars puts an enormous premium on where we already are. The solar system extends, roughly, to the Oort cloud, the vast reservoir of comets and icy bodies orbiting the Sun at distances up to about 100,000 astronomical units, or roughly 1.5 light-years. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 93 million miles. Out to about 50 astronomical units, the Kuiper Belt contains hundreds of thousands of icy objects. Pluto lives there. Eris lives there. Dozens of other dwarf planets we've discovered, and hundreds more we haven't. Out to several hundred astronomical units, the scattered disk extends, containing objects whose orbits have been perturbed by Neptune's gravity over billions of years. Out to the Oort cloud, an enormous spherical shell of trillions of comet nuclei, the source of long-period comets that occasionally fall inward toward the Sun. All of this is within our solar system. All of it is reachable, in principle, with fast propulsion. A subluminal warp drive would make the entire Oort cloud accessible. Missions to its inner edge would take hours. Missions to its outer regions would take days. The solar system, properly explored, contains more worlds than we've had the opportunity to seriously investigate. Before we spend centuries developing interstellar warp drive to reach a star 4 light-years away, the solar system offers more than enough to occupy a civilization for a very long time. This isn't defeatism. It's proportion. The interstellar ambition is real and justified and worth pursuing. But the immediate payoff of warp drive, if it ever becomes real, is right here. Not at Proxima Centauri. In the outer solar system, we've barely touched. The stars outside our solar system number in the hundreds of billions in this galaxy alone. The observable universe contains an estimated 2 trillion galaxies. The scale is genuinely incomprehensible. And every single one of those stars, every one of those galaxies, is separated from every other by distances that don't yield to ambition. They yield only to physics. And physics, so far, has not offered a clear path to making interstellar travel routine. It has offered a path to making it possible. Subluminal warp, properly developed, makes it achievable. Not convenient, not routine, not anything like the science fiction version that uses warp speed the way we use highway speed. Achievable in the sense that a crew could board a ship, survive the crossing, arrive at a nearby star, and potentially return within their lifetimes. That would be extraordinary. That would be one of the great achievements of our species. But the distance is still the distance. 25 trillion miles to the nearest one. And the one after that is farther. And the one after that is farther still. The galaxy stretches out for 100,000 light-years in every direction. And warp drive, if we build it, will close that gap one crossing at a time. Slowly, carefully, with enormous effort and resources and decades of transit. The stars are not going to come to us. Here is a dimension of the problem that often gets abstracted away. Fuel. Not in the abstract sense of warp drive needs a lot of energy. In the concrete sense of where does that energy actually come from, and what does carrying it cost? Every mission to space begins with a mass budget. You have a target, a crossing time, a required propulsion output, and you work backwards from those numbers to figure out how much total mass you need to launch. The rocket equation, formalized by Konstantin Tsiolkovsky in the early 20th century, describes the fundamental relationship. To increase velocity by a given amount, you need propellant in an exponentially growing ratio to payload mass. Double the required velocity change, and the propellant mass doesn't double. It grows by an exponential factor determined by the exhaust velocity of your engine. For chemical rockets, the exhaust velocity is limited by the energy released in chemical combustion. That gives you a specific impulse that caps out at a few hundred seconds for the best chemical fuels. Hydrogen-oxygen combustion is near the top of that range. Even so, reaching orbit from Earth requires roughly 80% of the total vehicle mass to be propellant. 800 kilograms of fuel for every 100 kilograms of useful spacecraft. Crossing to Proxima Centauri at any meaningful fraction of light speed makes orbital launch look trivial. Even with a fusion drive, which would have exhaust velocities millions of times higher than chemical combustion, the propellant mass ratios for an interstellar round trip are staggering. Getting to 10% of light speed, decelerating at the destination, accelerating for the return, and decelerating back at Earth requires propellant-to-payload ratios somewhere in the hundreds to thousands, depending on specific engine performance. That propellant has to be launched from Earth or manufactured in space. Either way, the cost is enormous. Warp drive changes this calculation in a specific way. The Bobrick-Martier framework showed that a warp bubble still needs conventional propulsion to get up to speed. The propulsion is pushing the bubble shell. The shell is accelerating. The crew inside feels nothing. But the energy is still being expended. And all of the constraints of the rocket equation still apply to the outer shell. The warp drive is not a free energy machine. It's a clever arrangement that makes the crossing more comfortable and potentially much faster. The energy budget for the crossing remains enormous either way. There's a historical pattern worth recognizing here. Every transformative propulsion technology has followed a similar arc. Someone identifies a physical principle. The mathematics is worked out. A theoretical framework is established. The framework reveals requirements that currently seem impossible. Then, over years and decades, and sometimes centuries, engineering catches up. Rockets weren't possible the moment Newton wrote down the laws of motion. They required 2.5 centuries of chemistry, metallurgy, manufacturing precision, and fluid dynamics before a working liquid-fueled rocket existed. Nuclear power wasn't possible the moment Einstein wrote E=mc². It required 40 years of particle physics, engineering, and industrial-scale manufacturing before a working reactor existed. The pattern is consistent. Fundamental physics comes first, usually far ahead of engineering capability. The gap between understanding and doing is filled by everything else. Materials, energy sources, manufacturing precision, control systems, the integration of dozens of technical fields into a coherent engineering solution. Warp drive is somewhere near the beginning of this arc. The fundamental physics is being worked out. The mathematical framework exists. Some of the basic theoretical questions have been answered. Subluminal warp doesn't require exotic matter. That much is established. The engineering is nowhere near starting. Not because engineers haven't thought about it, because the physics isn't fully resolved yet, and because the materials and energy sources the physics requires don't exist. We're at roughly the equivalent of 1905 for nuclear power. The principle is established. The pathway exists in concept. For nuclear power, the gap from 1905 to a working reactor was 40 years. For warp drive, the gap is measured in centuries. This doesn't mean we stop. It means we know where we are. Here is what's actually happening in warp drive research right now. The Applied Physics Group has published several papers establishing the theoretical framework. The Bobrick-Martier classification is the standard reference for describing and comparing designs. The Fuchs 2024 result demonstrated that positive energy subluminal warp is achievable in principle. Other researchers have built numerical tools for evaluating warp metrics. A software package called Warp Factory allows physicists to input a proposed spacetime geometry and compute whether it satisfies energy conditions, what matter distribution it requires, and how stable it is. This is real progress. It's the kind of systematic tooling that has to exist before engineering can even begin. Before you build anything, you have to map the design space. Before you map the design space, you need tools capable of exploring it at the required mathematical depth. Warp Factory is that tool. Papers on warp drive appear regularly in top-tier journals. Conference sessions on advanced propulsion draw larger audiences than they did a decade ago. The field is healthier than it has ever been. The engineering is still centuries away. Both things are simultaneously true. The research mattering and the result being distant are not contradictions. They are just the reality of where we stand in this particular arc of scientific development. The question of what the interior of a warp bubble actually looks like, what the crew experiences during the crossing, is one that the physics can partially answer. Inside the bubble, space-time is flat. Normal physics applies. Clocks tick at their standard rate. Light travels at its standard speed. The laws of thermodynamics hold. Food spoils at the normal rate. People age at the normal rate. From the crew's immediate perspective, they are simply in a room. A room that happens to be crossing 25 trillion miles. If the bubble geometry permits a view through the shell to the exterior, and this is an open design question, the crew would see something unusual. Not the clean star field of science fiction. At high fractional light speeds, relativistic effects distort the appearance of the sky. Aberration compresses stars toward the forward direction of travel. Doppler shifting blue eyes stars ahead and reddens stars behind. Inside a warp bubble, the geometry of the shell modifies these effects further. The view would depend on the specific metric, the exact mathematical description of the bubble's spacetime. It might be beautiful in unexpected ways, or it might look like nothing any human has ever seen. Either way, you'd know you were somewhere unprecedented, between the stars, in the void that no human has ever crossed. The crew members would mark days, keep routines, sleep and wake, cook food from stores, monitor the bubble's stability, check the drive systems, run experiments if they're scientists, exercise to maintain muscle and bone, talk, argue, reconcile, develop the kind of deep familiarity that comes from years in close quarters with a small group of people. The bubble doesn't remove the human dimension of the crossing. It just changes the physics dimension. The human dimension remains exactly what it would be for any long-duration, isolated mission. Demanding, psychologically complex, requiring careful selection and preparation, and without any precedent in human experience to draw on. Think about what it means for the crew to lose contact with the world they left behind. When Voyager 1 crossed the heliopause, it was already so far from Earth that radio signals took more than a day to make the round trip. The engineers at the Jet Propulsion Laboratory could send a command and wait roughly 17 hours just for the signal to arrive one way. That delay is significant by everyday standards. It's nothing compared to what an interstellar crew experiences. 1 year into a crossing to Proxima Centauri, the radio delay from Earth is 1 year. 2 years in, 2 years. By the time the ship arrives, 4 years of messages are backed up, waiting to be received. And 4 years of the crew's transmissions are waiting at Earth. If something goes wrong on the ship, a medical emergency, a mechanical failure, a conflict between crew members, Earth can't help in any real-time sense. The crew has to handle it themselves. This isn't a new challenge for space missions. Astronauts on the space station deal with emergencies autonomously. Ground teams support them, but the crew acts first because there's no time to wait for instructions. For an interstellar crew, the same principle applies, but with no possibility of evacuation. No emergency return vehicle. No rescue mission that could arrive in less than years. Whatever happens on the ship, the crew handles it with what they have. This enforces a kind of self-sufficiency that goes beyond what any existing mission has required. Medical training that goes far beyond what astronauts currently carry. Mechanical and engineering capability across every ship system. Psychological resilience for situations with no external resolution. The mission isn't just a physics and engineering problem. It's a human problem of the deepest kind. And warp drive, in all its mathematical elegance, doesn't touch this. Here's something worth understanding about the structure of interstellar space. The stars are not evenly distributed. They cluster in the plane of the galactic disk, denser toward the center, sparser toward the rim. Near us, the stellar density is moderate, a few stars per cubic region, about 30 light-years across. The Sun sits in a region called the local bubble, a roughly spherical void about 1,000 light-years across, carved out by a series of supernova explosions millions of years ago. The gas density inside the local bubble is lower than the average interstellar medium. This means the space immediately around us is relatively empty, even by interstellar standards. Beyond the local bubble, the interstellar medium is denser. Molecular clouds, dense regions of gas and dust, where new stars are forming, are scattered throughout the disk. Active star-forming regions like the Orion Nebula, which contains thousands of young stars still embedded in gas and dust, are about 1,300 light-years away. The center of the galaxy, with its dense concentration of stars, ancient globular clusters in tight orbit, and the supermassive black hole Sagittarius A at its core, is 26,000 light-years away. A warp ship crossing from Earth to the galactic center at 95% of light speed would take about 27,000 Earth years. From the crew's perspective, due to time dilation, somewhat less. But Earth would have aged 27,000 years regardless. Civilizations rise and fall on timescales of thousands of years. A ship sent to the galactic center would be a message in a bottle, launched by a civilization that might not exist in any recognizable form by the time the ship arrived, or by the time any return signal reached home. The galaxy is big in a way that no propulsion technology, however advanced, fully addresses. It's a constraint on what interstellar civilization looks like at the deepest level. You can travel fast. You cannot travel fast enough to keep the galaxy accessible on human timescales. The physics doesn't give you that. Let's look at the Fermi paradox from a slightly different angle. The standard framing asks where the aliens are. But a more specific version of the question is, if warp drive is possible, why haven't we seen evidence of civilizations using it? Warp drive, particularly a superluminal version, would leave signatures. The space-time distortions involved would produce gravitational wave emissions, possibly detectable from large distances with sufficiently sensitive instruments. The compression of space ahead of a superluminal bubble would interact with the cosmic microwave background in specific ways. The radiation burst produced when a superluminal bubble decelerates. The Finazzi-Liberati-Barcelo effect would produce a distinctive, high-energy signature. If civilizations were regularly crossing interstellar distances with warp drives, and if we had been listening for the right signals, we might expect to see something. We don't. This is not evidence that warp drive is impossible. It's evidence that either no civilizations are using it, or they're using it in ways that don't produce detectable signatures, or the signals exist and we haven't found them yet, or our instruments aren't sensitive enough. All of these are possible. But the silence is consistent with a universe where interstellar travel remains rare or impossible, even for advanced civilizations. The more advanced a civilization becomes, the better it understands the constraints. And the constraints are severe. A civilization that truly understood the physics might conclude that the resources required for interstellar travel are better invested elsewhere. That the return on investment In terms of scientific knowledge, expanded civilization, resource access, doesn't justify the enormous cost. That staying home, perfecting life in your own solar system, is a rational strategy given the physics of the universe. This isn't defeatism. It's what the numbers might tell you if you run them honestly. The Fermi paradox doesn't require a dramatic explanation. The distance between stars might be sufficient by itself. Now let's return to where this all begins. Not with the equations. Not with the physics. With a clear night and a sky full of stars. Every star you see is a sun. Most of them are larger than ours. Most of them are older. Many of them almost certainly have planets. Some of those planets are in the right temperature range for liquid water. Some of those planets have been there for billions of years. And you are looking at them from a distance of light years, using photons that took years or centuries or millennia to cross the void between you and them. You will never visit most of them in your lifetime. Not because you lack the will, not because civilization lacks the ambition, because the distance is what it is. Light covers it in years. Nothing else has been demonstrated to do better. Everything we know about physics suggests that beating light speed, if it's possible at all, requires overcoming barriers of exotic matter, causal horizons, and energetics that we don't yet know how to solve. And everything we know about the subluminal path suggests that even the best-case warp drive produces years-long crossings to the nearest stars. This is the honest picture, not the despair picture, not the defeatism picture, the honest one. The distance between stars is a real constraint on what interstellar civilization can be, not an obstacle waiting for the right solution. A property of the universe we live in. And understanding that property is the beginning of understanding our actual place in the cosmos. Not the imagined place of science fiction, where the galaxy is a neighborhood, the real place. A species on a small planet orbiting an ordinary star, 4 light-years from its nearest neighbor, embedded in a galaxy so large that even the fastest thing in the universe would take 100,000 years to cross it. That's where we are. That's what we're working with. And the research happening right now in journals, at conferences, in software tools built to map the mathematical design space of warp drives, is humanity's current best response to this constraint. Not a solution. A response. A sustained, disciplined, honest engagement with a problem that doesn't yield easily. The kind of engagement that has produced every major advance in science and technology across the history of our species. The kind that takes longer than any individual career. The kind that requires civilizations, not just scientists. The kind that starts with understanding the problem before reaching for the solution. And the problem starts with the distance. It always starts with the distance. The materials and engineering challenges deserve a moment of honest description, separate from the physics. What does it actually take to build a warp shell? The shell has to maintain a precise geometric configuration, a specific distribution of mass and energy that produces the desired spacetime curvature for the entire crossing. It has to resist the interstellar medium pressing against its leading edge. It has to handle extreme temperature differentials. The side of the shell facing the direction of travel interacts with interstellar gas and radiation. The side, trailing behind, faces the thermal void of deep space. The temperature difference across the shell could be enormous. It has to remain structurally intact under the gravitational stresses produced by its own curvature geometry. It has to do all of this with no possibility of major repair or replacement for the duration of the mission. There are no service stations between stars. Materials science on Earth produces extraordinary things: carbon fiber composites, titanium alloys, advanced ceramics, graphene and its various derivatives. Materials with strength-to-weight ratios that would have seemed impossible to engineers a century ago. None of them are remotely sufficient for what a warp shell would require. The stress regimes are qualitatively different from anything we encounter in conventional aerospace engineering. We don't have laboratory tests that simulate what a warp shell would experience in operation. We don't have design specifications because we don't have enough understanding of the shell's behavior at operating conditions to write them. We don't know what failure modes look like because we've never built anything approaching a warp shell. This isn't an argument that it can't be done. It's an honest description of where we are in the engineering. The gap between what we know and what we'd need to know is vast. It's not the kind of gap that closes in a decade of focused research. It's the kind that requires fundamental advances in multiple fields simultaneously over timescales that dwarf any individual research program or any single generation of scientists. Here's a thought experiment that reveals the scale of what we're attempting. Imagine you're living in the year 1800. Napoleon is reshaping Europe. The steam engine is a recent invention, and people are just beginning to understand its implications. There are no telephones, no electric lights, no internal combustion engines, no aircraft, no radio. Germ theory hasn't been developed. The atom is a philosophical concept, not a physically confirmed particle. Einstein hasn't been born yet. Now imagine telling someone in 1800 that within 200 years, their descendants would build a machine that uses the nuclear force binding protons and neutrons together inside atoms to heat water, drive turbines, generate electricity, and power entire cities. That their descendants would also build machines that use the same nuclear force to produce explosions thousands of times more powerful than any conventional explosive. And that these machines would require understanding matter at the scale of 1/10,000 trillionth of a meter. That person in 1800 would have no framework for understanding what you're describing. The science doesn't exist. The instruments don't exist. The mathematical tools don't exist. The industrial infrastructure doesn't exist. And yet, 200 years later, nuclear power and nuclear weapons are real. The gap between 1800 and 2026 is roughly the gap between where we are and where warp drive engineering begins. Not where warp drive is built, where the engineering starts to become tractable. 200 years of development, possibly 3, possibly more, but the direction is established. The physics points toward a real thing. The engineering will eventually follow. Slowly, certainly not on any timeline that any of us alive today will see completed. But eventually, one more thing about the interstellar distance problem that doesn't get said enough. The distance isn't the enemy. It's the context. It's the frame within which everything about interstellar civilization takes shape. The distance between stars means that every system is effectively self-contained. The light from a stellar explosion at Proxima Centauri would take 4 years to reach Earth. The gravitational influence of a rogue planet passing through the Alpha Centauri system would take millennia to meaningfully affect the Sun. The stars are isolated from each other in almost every relevant physical sense. They burn independently. Their planets develop independently. Whatever life arose on some planet around a distant star developed in complete isolation from whatever life arose here. The distance enforces a kind of cosmic individuality. Each solar system is its own experiment. Each planet its own petri dish. Each civilization, if there are others, its own unique product of specific local conditions. There's something profound in this. The universe is not a place where everything is connected and mutually influencing. It's a place where islands of order, solar systems, planetary systems, living worlds, sit separated by such enormous voids that they develop in almost complete independence. The distance between stars is what makes each of those islands what it is. It's what allowed Earth to develop life over 4 billion years, without interference from whatever is happening 4 light years away. It's what allows the sun to shine without being significantly affected by the stellar winds of its nearest neighbor. The isolation is not a flaw in the design. It's a feature of the physics that allowed complexity to arise. Stars need space to form. Planets need stability to develop. Life needs time, uninterrupted. The distances provide all of this. And the price is that the universe is hard to traverse. That is not a coincidence. It is the same physics operating on different scales. The distance between stars is not the universe's mistake. It's part of what makes the universe work. Every time we extend our reach from the cave to the valley, from the valley to the continent, from the continent to the planet, from the planet to the moon, from the moon to the solar system's edges, the scale of the next step has always felt impossible. And then, eventually, it wasn't. The oceans felt impossible until they weren't. Flight felt impossible until it wasn't. Orbit felt impossible until it wasn't. The interstellar distance feels impossible, and it might remain impossible for a very long time. But the mathematics of warp drive says it isn't forbidden. The physics says the universe hasn't locked the door. It's just made the key extraordinarily difficult to manufacture. That's the honest assessment. Not a promise. Not a guarantee. A recognition that the problem is real, that progress is being made, that the gap is large, and that the distance, that stubborn, patient, unchanging distance, will be exactly what it is on the day we find a way to cross it. If we do, the stars will wait. They always have. The Milky Way has been forming stars for about 10 billion years. Our Sun is about 4.5 billion years old. It formed in the second half of the galaxy's stellar history, after the first generations of massive stars had lived their short lives, collapsed, and exploded as supernovae, seeding the interstellar medium with carbon, nitrogen, oxygen, iron, and every other element heavier than hydrogen and helium. Without those earlier stellar generations, there would be no rocky planets, no carbon-based chemistry, no biology. Our Sun is a third-generation star, and the complexity of our world depends on everything that came before it. Other stars in the galaxy are older. Some formed 8, 9, 10 billion years ago, when the universe was young and the galaxy was still assembling itself. Stars that have had billions of years longer than our Sun to produce stable systems. If planets formed around those stars, and the evidence from exoplanet surveys suggests planets are common around most stellar types, some of those planets might have had billions of years longer to develop whatever they were going to develop. Life, if it arose on such a world, would have had a head start of billions of years on whatever life exists on Earth. A civilization arising on such a world, 1 billion years older than ours, would have had 1 billion years more to work on the interstellar travel problem. 1 billion years of physics. 1 billion years of engineering. 1 billion years of thinking about the distance. And the distance is still the distance. Whatever they concluded about it, whether they cracked it or decided it was fundamentally uncrossable or found a third option we haven't thought of, they faced the same constraint we face, the same photons, the same light speed limit, the same equations. The universe is consistent. It applies its rules everywhere. The distance between stars that challenges us today is the same distance that challenged whoever came before us, whenever and wherever they arose. And here is the last thing to hold on to before the closing. The research is real. The mathematics is valid. The 2024 Fuchs paper is in the literature, peer-reviewed, standing. Subluminal warp drive is not exotic matter science fiction anymore. It's a class of solutions to Einstein's field equations that satisfies every classical energy condition using ordinary matter with no forbidden physics anywhere in the structure. That is a real and important result. The people working on this problem are not dreamers in the pejorative sense. They are mathematicians and physicists doing careful, rigorous work in established journals, building a foundation that didn't exist 30 years ago. The field is real. The progress is real. The engineering gap is real. The distance is real. All of these things are simultaneously true. And holding all of them together, the ambition and the honest assessment, the progress and the remaining barriers, the mathematics and the miles is what it means to look at this problem clearly. The stars are 25 trillion miles away at the nearest. Warp drive might make that crossing achievable. Probably will, eventually. But it won't make it fast by everyday standards. It won't make it easy. It won't make the galaxy feel small. It will make the crossing survivable within a human career span, which is extraordinary. It will connect us to the nearest stars in a way that nothing currently on the shelf can do. But the distance remains. It has always remained. It will remain. And every honest conversation about reaching the stars starts there, with the distance, not with the ship. There's one more physics problem with superluminal warp that rarely gets discussed. And it goes to the heart of why physicists are cautious. Causality. Einstein's special relativity and the light speed limit aren't just rules about how fast things can go. They're the framework that makes cause and effect relationships consistent across the universe. If information can travel faster than light, it can also, under certain combinations of motion, travel backward in time. Not in the sense of dramatic time machine cinema. In the sense that an observer moving at high speed relative to the ship would detect the ship's departure signal after the ship had already arrived at its destination. Cause following effect. The order of events becoming ambiguous. This creates what physicists call causality paradoxes. Situations where a signal sent from the destination could, in principle, arrive at Earth before the ship even departed. If you can send information backward in time, you can potentially change the past. And if you can change the past, then the chain of causation that led to you sending the message in the first place might be altered. The logical structure of the universe starts to break down. Now, Most physicists believe the universe has some mechanism that prevents this. Some deeper physical law that steps in before causality paradoxes can actually occur. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent closed time-like curves, paths through space-time that loop back to their own starting point. But this conjecture hasn't been proven. It's a reasonable expectation based on how physics seems to behave, not a demonstrated theorem. Superluminal warp drive, if it ever becomes achievable, might run into chronology protection as a hard limit. The universe might simply refuse to allow it, in ways that current physics can't fully predict. This is another layer of the interstellar distance problem that the engineering approach can't solve. You can improve the exotic matter problem. You can work on the horizon problem. You cannot reason your way around the fundamental structure of causality. If causality protection is real, and most physicists expect it is, then superluminal travel isn't just difficult. It's forbidden in a deep sense. Not by an arbitrary rule, by the logical self-consistency of the universe. That's the version of the interstellar distance problem that no amount of clever engineering ever reaches. The distance remains. It always remains. And the physics we know is mostly telling us that crossing it quickly is going to be one of the hardest things our species has ever attempted. Not impossible, but hard in a way that humbles every timeline and every promise. The distance between stars is the physics problem that launched warp drive research in the first place. Alcubierre looked at the numbers and asked whether the universe's geometry could be used to sidestep the constraint. 3 decades later, the answer is partially yes. Subluminal warp, yes. Faster than light, still unresolved. The research produced real results. It also confirmed something the distance was always trying to tell us. This isn't easy. It was never going to be easy. The stars are far apart. The physics knows it. And so do we. That is where the honest conversation ends, and where the next century of physics begins. The question of whether warp drive will ever be built is ultimately a question about civilizational patience. The physics took 30 years to reach the point where a positive energy subluminal solution could be demonstrated. The engineering will take centuries more. No single person, no single institution, no single generation will see this through. It's the kind of project that requires passing down not just knowledge, but commitment. The conviction that the stars are worth reaching, even if reaching them takes longer than any individual life. Science has done this before. The search for gravitational waves began with Einstein's prediction in 1916. The detection came 99 years later, in 2015. The researchers who detected them were not the ones who predicted them. They were not even the grandchildren of the ones who predicted them. But the chain of knowledge held. The instruments improved. The commitment persisted. And on September 14th, 2015, 2 detectors in Louisiana and Washington simultaneously registered the faint ripple of spacetime from 2 black holes merging more than 1 billion light-years away. The signal lasted about 1/5 of a second. It confirmed general relativity in one of its most dramatic predictions. Warp drive research is earlier in that arc. Much earlier. The prediction exists. The theoretical refinements are happening. The experimental tools are primitive. The confirmation is far away. But the chain is holding. Papers are being written. Researchers are building on each other's work. The commitment is persisting. And whatever the outcome, the engagement with the problem is real. Look up on a clear night. Find the brightest star you can see. Whatever it is, Sirius, Vega, Arcturus, Rigel, it is years away. The light hitting your eyes right now left that star years or centuries or millennia before it arrived. You are not seeing the present. You are seeing the past, traveling at the maximum speed the universe permits, crossing distances your brain can do the mathematics on, but cannot viscerally feel. The star you're looking at might not even exist anymore. You wouldn't know for years. Warp drive might shorten the crossing time to that star. It might make what currently takes 70,000 years take 5. That would be extraordinary. That would be one of the greatest achievements in the history of science and engineering. But the distance remains. 25 trillion miles. Not a barrier placed there by accident. A feature of this universe. Settled into the structure of space, the way physical constants are settled into the laws of nature. Not something that yields to wanting it to be different. The honest conversation about reaching the stars has to start here. Not with the ship. Not with the engine. Not with the beautiful mathematics of curved spacetime. With the distance. Because the distance is what everything else is a response to. And every honest response, no matter how mathematically elegant, no matter how physically valid, no matter how many peer-reviewed papers support, it still has to cross it. Mile by mile. Year by year. One crossing at a time. The equations are beautiful. The universe is patient. And the space between the stars will be exactly as large as it is today on the day we finally find a way to cross it. If we find the way. And if we do, it will begin not with a button press and a flash of light, but with decades of physics and materials, science and engineering and power generation and testing and iteration and failure and refinement. And then finally, one day, a bubble of flat space-time accelerating away from a solar system that suddenly feels just a little smaller. Just a little. The stars will still be far. They will always be far. That is the truth that warp drive cannot change. And knowing it doesn't diminish the ambition, it gives the ambition its proper weight. Thank you for spending this time with one of the deepest problems in the physics of the future. If this shifted how you think about warp drive, about the stars, about the honest gap between what the mathematics allows and what the universe will actually give us, then the time was well spent. A like or a subscribe helps this channel keep making these deep examinations of our place in the cosmos. And the next time someone tells you warp drive solves the interstellar distance problem, you'll know the complete answer. It might solve part of it. The part about speed. The rest of it, the energy, the materials, the physics still unresolved, the human cost of years in the void, and the simple, stubborn fact that the stars are exactly as far apart as they've always been, that part is still waiting. The equations don't change this. The physics doesn't soften it. The distance between stars is the price of living in a universe where stars exist at all. And we are learning, slowly, to pay it. The universe doesn't negotiate. And the distance between stars is its most patient argument. Good night.